Okay, my name is Wieger Wesselink. I'm going to talk about an application of Dafny' to Minimax search. It's joint work with Kees Huizing, who's also present here, and Huub van Wetering. I'm first going to explain the problem domain, the foundations of game tree search, and specifically about the verification challenge. And afterwards I'll talk a bit about our experiences with Dafny'. The setting is we're looking at two-player games where zero-sum games, so the gain for one player is a loss for the other, alternating moves, and we really look at trees, so there cannot be cycles in the game. And we can model that using game trees. So we have just the nodes are game states and the arrows are moves, and then we have a playout is just a tree, and in the leaves we know the results, these are just numbers. And then we assume there's optimal play for both players. One player tries to minimize the score, the gray nodes, and the white nodes is a maximizer. And then you can just bottom up compute the game tree value for the root by just depending on the minimizing or maximizing player, taking the minimum or the maximum of the children. A well-known classic algorithm to compute that value is a recursive algorithm called Minimax. It just goes top-down through the tree and evaluates the children and then recursively computes that result. Negamax is just a shortened version of Minimax, and that's one is used in practice a lot. That's the one we will focus on. And we will add 3 practical features to it to make it more interesting. And these are alpha-beta pruning, depth-limited search, and the usage of transposition tables. This is used in practice a lot. There's a lot of subtleties with these algorithms. They are not fully understood, and we try to verify them using Dafny'. So I'll explain these 3 features first. Alpha-beta pruning is a way to increase efficiency. It's based on we expect the value to be in a certain interval alpha-beta, and inside that alpha-beta interval we want to have exact results, so a true negamax result. If the result is to the lower than alpha, then we are satisfied with knowing that it's just an upper bound, or on the other hand it can be a lower bound if it's to the right of beta. So we can have 3 different outcomes, an upper bound, an exact value, or a lower bound. And this helps to prune a lot of unnecessary parts of the tree. Second feature we add is depth-limited search. That's just, in practice, these game trees are so huge that you cannot compute all the way to the leaves. So we just stop the search at some depth limits, and then we use that to evaluate the result. That means that we also need values for the internal nodes, not just for the leaf nodes. So usually people use some heuristic to give a value to the internal nodes. And the last feature we will focus on, that's the most important one, is using transposition tables. The idea is that for game states, we do not want to have repeated evaluations. The same game state can occur many times in the same game tree, and you want to reuse those results by caching them in a table. And what people typically store is the value of the search and the depth that was corresponding to that search, but also the kind of the search from the alpha-beta result. Is it a lower bound, an exact value, or an upper bound? Note that the alpha and the beta themselves are not being stored, so it's not a complete result, but that's what people use in practice. And we are going to look at 2 different algorithms with those settings. One is a classic algorithm from Marsland from 1986, and that uses those 3 features, and the other one is the current version on Wikipedia. And they have, I'll first show you, there are 4 differences between those 2 algorithms, but I will only focus on the first one. And let me go back to explain you a bit about the structure of those 2 algorithms. Note that there are 3 different phases when you use a transposition table search. The first phase, the top one, is the table lookup. You're searching a node U, and first you check, is it in a table? And if so, we can use the table result either to return directly or do something with it. The second part is just the negamax search. You do the negamax algorithm, and the last part is you get a result from the negamax algorithm and you use it to update your table, your transposition table. Now, it turns out that there's an important difference in the table lookup. If you look at the Wikipedia version, let's go there first, that is a very conservative approach. We just look at the table, check if the depth is big enough, and then we can use it. And if it's a good result, we just return it and stop. So then we're done. Otherwise, we just do a normal search. But now the Marsland version does something different. It does also do lookup in the table, check the depth. If it's exact, we're done. But if it is an upper bound or a lower bound, Marsland says, no, I'm going to shrink the alpha beta interval. I'm trying to get an exact result, so I'll continue the search with a lower depth. It seems to make sense, but it turns out that this really affects the correctness. The other three differences, it turns out they are more or less optional. We can just apply them in both algorithms or not and still prove correctness. What's important to realize is that actually the correctness of these algorithms is undefined. Nobody has ever specified, at least to our knowledge, what correctness means when you use a transposition table. So that is an important part of the verification. People in practice also talk about this a lot, all these differences, but anyway, that's just, it's very subtle and people have all kinds of opinion about what is correct and what not. So that gives also motivation for doing this kind of research. So now the most important part of our work is just, we have tried to define a correctness criterion for transposition table search. First I'll give you an intuition what that means. And our idea was, well, that result is unspecified what it means, but we think there should be some kind of game tree that explains the result, such that a game tree has a negamax value that is equal to the result of the transposition table search. And why do we think that is the case? For that we look at what does a transposition table search look like? Well, it is a depth limited search, so the left picture shows the nodes until that depth limit. Those are being searched normally. But if you have a transposition table hit, it's shown in the second picture with a black dot, then you just have a lookup and you do not explore the results below. So those ones are skipped. But if you think about it, it's a transposition table result, maybe at a higher depth, and there were also nodes contributing to that search. So if we plug those nodes in, we get a picture on the right. These are all the nodes that have contributed to the search, and that can even happen recursively. So that transposition table search here can also have used the transposition table before. So it really becomes that kind of wild structure. But our hope is that this gives us a game tree that explains the result of the algorithm. And to formalize that, we made some criteria for what we call that game tree a witness. And we formulated, say 4 requirements for what a witness is. So we want it to be a subtree of the original tree. It should have the same negamax value. It should also be it should include the full tree until depth D, because we have a search of depth D. And lastly, that's more for soundness, if we have a node in a witness, it should include all the children of the original node or none, but not just a selection, because then you get very weird trees that correspond in no way to Minimax. So you have either all children or you just leave them all out. This was our criterion. We applied it to that 2 algorithms that I showed. The Wikipedia version we managed to prove correct using this. It was about 800 lines of code and verified in 4 seconds. But the Marsland version, we did not manage to prove it, and actually we managed to show that it violates our witness criterion, so it does not satisfy it. And for that, Dafny was actually quite helpful, because we almost managed to prove it. There were just 2 configurations where the post condition we were unable to prove it, and this is just one of them, where we have the initial alpha value was moved to the right because of a lower bound hit in the transposition table, and the end result was between those alpha values. That was the difficult problem, and this inspired us, to look at this as a possible counterexample, we managed to get a concrete search tree that really showed that that this Marsden algorithm does not satisfy the witness criterion. We have a window of 0.5, we have this small tree, and we have search depth 2, and we have a table that's already filled with a lower bound at depth 3, so a higher depth. And this was quite a puzzle, but we found it based on those hints from Dafny'. Now, why is this a problem? The two problems. One is that the return value is 2, and that really is not a minimax value, because the parent of the node 2 is a gray node, is a minimizing node, and you should expect at the between the depth level that it should always minimize, so return the node 1. But because of that table hit, the window has been shrunk to 3.5, and then 2 is outside the window, and the result, the node 1 will not be visited. So it's a questionable result. But moreover, it also does not, there is no witness game tree that results in the value 2. It does not exist. If you extend this depth level to 3 with the nodes 3 and 4 or not, the result is always 1, 3, or 4, but never 2. That's not there's no witness that results in 2. So really this example shows that the criterion does not hold. We actually managed to extend this example to a search that starts with an empty table. So then it includes the previous example. So this shows that Marsden does not satisfy our criterion, which we thought was quite natural. Okay, so now the last couple of minutes I will briefly explain some experiences with Dafny'. Well, the modeling in Dafny' was quite concise. We were very pleased with it. We did, it just looks like this. We have bounded integers as a constrained data type. These are just the predicates for describing the witness. Also, we not only need to look at the result value, but also we need to look at the transposition table that should also only contain results for which a witness exists. So we see that here, that in the transposition table should also be required. Yes. Well, here we have the expansion predicate that is part of that witness. We managed to define it without relying on other predicates, so it's really self-contained. That helped a lot. We have been improving all kinds of properties and put them in lemmas, like it should be reflexive, it should be transitive, it should have include the depth limited part, and all these things that could even be proven automatically using Dafny'. A very major issue was the proof stability. The specification contains a lot of quantifiers, and then you typically get symptoms like memory exhaustion, like in 15 seconds your whole memory is taken, you can reboot, and that happened countless times. And also that the verification sometimes doesn't terminate. What did we do to avoid, mitigate that? We avoided inline proofs wherever we could. Always use lemmas instead of inline proofs. Also put lemmas at strategic places, sometimes where you thought it should not be needed, but just do it. I will give you an example soon. Keep the formula small. If you have a large formula, put subparts into predicates. And as a last resort, use opaque predicate to hide the definitions. Here we see an example of these lemma calls. So just in front of at the end of a loop or in front of a break, that's a place where proof obligations hold. We insert a lemma. And actually this happens a lot. If you change the invariance, you need to do it again. I would really like to have a feature that Dafny' helps me to generate a stub for such a lemma, because it's a tedious job. You need to do all kinds of calculations to find the exact state at that point where you call the lemma and put them in the requirements. I think it can be automated and it would be quite helpful. Finally, let's skip this. There's also functional programming. Let me wrap up with the conclusions. We introduced that witness-based correctness criterion. We verified the practical algorithm that's non-trivial. We did 15 to 20 more of these algorithms. And it really shows that Dafny is a good tool for doing this kind of research. Thank you.
Talk. I'm wondering, do you have any assumption on the heuristic that you use when you reach the depth? Is there some correctness assumption about the heuristic that when you haven't yet fully explored the tree, but you have to stop at depth 3 or something?
No, the thing is, if you do depth-limited search, you have no guarantee whatsoever about the result. It can be arbitrarily bad, because it really depends on the quality of those heuristic values, and they can be so bad that every winning position can become a loss, so you can't help that.
In this case, what does the correctness criterion that you introduce help you with? What does it tell you other than can be arbitrary?
No, it gives you at least an intuition for what does that value mean. Well, we can construct a game tree that relates to the search and that explains the result. So that game tree that you extract in isolation gives a negamax result with the same value as your transposition table search. So it gives you an interpretation of the result.
One last question while the next speaker is coming to plug their computer.